So in today's class, we shall be starting with generating functions, which is basically the third chapter of CS1. Here, what we're going to look at is certain tools or certain functions which we define and which can be further used to calculate various quantities of a probability distribution in a more efficient manner. So we will be, let's say using certain functions, as the name suggests, generating functions. We'll see there are few types of it. We will try to calculate, let's say, the mean, the variance, the skewness, expectation x square or expectation x cube, so on, using these functions. As against deriving these quantities through first principle, we will see that deriving these quantities through this particular function becomes a lot more mathematically easier. So in examination, unless otherwise explicitly mentioned to derive from first principles, what we are going to see that is we are going to take help of these generating functions to calculate the mean, variance and skewness, because the calculation or derivation of these would be a lot more easier using these particular set of functions. So the chapter, I would say, is an extremely easy one. It's a very scoring topic as such. Once you get the essence of the three different type of functions which we are going to describe, its application part, I would say, is rather way easier compared to the other chapters which we have in CS1. So just give the heading introduction. Give the heading introduction. So write down generating functions. Generating functions provide a neat way of working out. Provide a neat, N-E-A-T, neat way of working out various properties of probability distributions without having to use integration repeatedly. Without having to use integration repeatedly. Full stop. For example, they can be used to. For example, they can be used to first point, find the mean variance, find the mean variance and higher moments of a probability distribution and higher moments of a probability distribution. Second point, find the distribution of a linear combination of independent random variables. Feel free to use the short form RV, which denotes random variables. Comma, example x plus y. Comma, example x plus y. And the final point, determine the properties of compound distributions. Determine the properties of compound distributions. This is covered in subject CS2. This is covered in subject CS2. Now, again, one more thing. If you would refer to the past year papers, I hope you all do remember by today that, before 2019, instead of CS1, the paper which we had was basically CT3. And also in CS2, in CS1, some parts of CT6 paper have also been incorporated. So previously there was a topic called compound distributions, which was part of the CT3 syllabus. It's no more a part of CS1 syllabus. It is a part of CS2 syllabus. So the third point basically covers that whenever we try to look at the properties of compound distribution, using generating functions helps us achieve this. So again, in CS1, we are not going to cover compound distributions. When you practice, say, the CT3 papers, of 2019 or earlier, be it from IFOA or II, you could skip those questions because those aren't a part of our syllabus of our CS1 syllabus anymore. So that was just one thing to keep in mind for future reference. Now, one question which a lot of you might have, and that is very fair to have, is that in today's session we would be defining certain functions. You might have a question, who invented this function, from where did it come? So honestly speaking, it's just a matter of imagination for these mathematicians or statisticians who came up with these quantities, because the ultimate aim was to simplify the calculation, be it calculation of mean, variance, so on. So it's not a matter of who started it. It's more about there was a problem wherein where one had to make summation or integration again and again to calculate mean, variance, or even higher expectations. To overcome this problem, let's say genetic functions was a solution. Now if you expect that you or a lot of us, or even me myself, can come up with these ourselves, it might be very challenging. So that is just the ones who are into the subject, they knew where to begin with, how to come up or invent such functions which could have such let's say applications which kind of makes a lot of calculations easier. So what we are going to do is we are going to look at three functions. One of them is not a part of our syllabus anymore, but for completeness of this topic we would be covering that, and then we will see structurally how from one function to another we go, and what are the, let's say, each like if I start with the first function, there would be certain shortcomings of it, mostly with respect to the efficiency of calculations required. Then we move on to the second function. We will see it is a lot more efficient compared to the first one, and then we'll move forward to the third function, which we will see is a lot more efficient. When I say efficient, what I mean over here is only with respect to calculation of primarily mean, variance, and skewness. Number of steps involved to calculate this will progressively decrease as we move from the first function towards the third function. So basic formulas remains the same. For each individual probability distribution, the final result will be coming out different. So this was a basic introduction. Now to come up with the three functions which we would be covering in today's session. First of them is known as, which is not a part of our syllabus anymore, but yet we would be doing that for completeness of this topic. Is probability generating function, and let's say we denote the short form for this right now to be PGF. Next one, what we have is a moment generating function, referred to as MGF, and then finally we have a cumulative generating function. Probability generating function is only defined for discrete random variables. The other two are defined for both discrete as well as continuous. MGF and CGF are very much a part of our existing syllabus. PGF is no more a part of current syllabus, yet I'm going to teach that and you all are expected to know, because it's not a very difficult thing, and for completeness you all should know about this particular function as well. It was a part of our syllabus before 2019 though. So now give the heading probability generating function. Probability generating function. Right now, this function can be used to calculate probability, comma mean, comma variance, comma skewness, etc. for only discrete distributions. For only discrete distributions. Now, it will make sense as the name suggests probability generating function. In case of continuous random variables, we did studied that there is no probability at a particular point. Probability for a continuous random variable at any single point is nothing but zero. We can find probabilities for a range or for an interval, but not for a single point. Therefore, the moment I define a function which helps me to calculate probabilities, so it must be only for a discrete random variable, not for a continuous random variable. And when I say probability here, I refer to probability at a point and not probability between a range of values. So now next is the notation part. How let us we denote it to be. We denote it to be pxt or gxt. So you can write it is denoted by pxt or gxt, and this is nothing but expectation of t to the power x. Which comes out to be summation t to the power x into probability x equal to x for all values of x. Now, could you all just tell me from the structure, this pxt, this will be a function of what? Which variable? The ones which I've used on screen, it is finally going to be a function of which variable? Either x, either t, or both x and t. Take a look at it and think about it. Three options you will have, either x, either t, or both x and t. My question is, the function which we get here will ultimately be a function of which variable? T, x, or both of them? X. Okay, one of you suggesting both, one of you suggesting x. Let's look at the others. Okay, one of you has mentioned to be t. Again, an option of both comes. X and t. Okay. Okay, so the correct answer first of all is that it will be a function of t only. And for the reason of that is, if you'll take a look at the summation, you might see an x over here right now, fine. But when you simplify this, these are for all values of x. So ultimately, I'll have t to the power something into a probability, which will be a constant value. It won't be a function of x, it will be some constant value. So this entire result will be nothing but a function of t only. And we will shortly see, when taking certain examples, that might make it even more clear to you in case the general formula does not give that particular result. So we will take a look at that as well. Now after this, again write down PGF can be used to generate a set of probabilities namely the probabilities associated with the values, 0, 1, 2, so on. Full stop. Alternatively, cut down alternatively. In other words, we will only define PGF. For those discrete random variables, which takes non-negative integer values. Now let us, if I try to kind of expand this. Now here x, it is for all possible values of x. Now we have restricted ourselves that x can take the values 0, 1, 2, 3 and so on. So if I put x as 0, the first term will be nothing but t to the power 0 into probability x equal to 0. T to the power 0 is nothing but 1. So the first term is going to be probability x equal to 0. Next term, when I put x equal to 1, it will be t into probability x equal to 1. Next term will be t square, probability x equal to 2 and so on. If any of the probabilities are 0, then you will see that particular term will get vanished out. This becomes my general expansion. Now, let us try to look at few properties. If I put t as 0, if I put t as 0 over here, what do I get from this expansion? All terms which have t shall become 0. We will be left out with what only? Probability x equal to 0. If I take the value of t to be 0, all these terms will come out to be nothing but 0 over here. So, one result which I can write is px0 is nothing but probability x equal to 0. And let us take t as 1. It will be probability x equal to 0 plus 1 into probability x equal to 1 plus 1 square into probability x equal to 2, so on. So basically it will be probability x equal to 0 plus probability x equal to 1 plus probability x equal to 2, so on. All these probabilities add up to give us what? X greater than equal to 0, which is nothing but 1. We are basically adding all the probabilities over here. The only values which the random variable can take is the non-negative integers. We are adding all those probabilities. So that will give us nothing but 1. So these are two results. And note, I have expanded it and then try to make you all understand. Another way to understand this, to sum it, one method might be easier than the other. Another is to just take a look at the summation form. When I put the value of t as 0 over here, okay, so forget t equal to 0. Let's say when I put t equal to 1 over here, 1 to the power x for all values of x is nothing but 1. So we are left with nothing but summation probability x equal to x for all values of x, which is nothing but 1 over here. And similarly, if we'll try to put as 0, then just remember that we'll have a form 0 to the power x. When x is 0, 0 to the power 0 is something which is not defined. 0 to the power 0 can take different values. So to understand probability, px0, don't try to take it of the form summation of 0 to the power x, because it will fail down when you not try to find the let's say the numerical value of 0 to the power 0. So that is why I have shown you two approaches. One is using expansion, another is using summation, so that visualizing these things becomes easier. Now this is this. Next, write down coefficient of. These are the first 2 points. Third point, coefficient of t to the power k. Coefficient of t to the power k is probability that capital X takes the value k, small k. As you can see from the expansion here, the coefficient of t is nothing but probability x equal to 1. Coefficient of t square is nothing but probability x equal to 2. So coefficient of t to the power k will be nothing but probability x equal to k. Now take down this question. Derive the PGF for the below random variable. Derive the PGF for the below random variable. So all of you give this a shot yourself. It's a very easy question. So using the formula here, by derived means you just need to start with the formula. It is expectation of t to the power x, which will become t to the power 0 into probability x equal to 0 plus t to the power 1 into probability x equal to 1 plus t to the power 2 into probability x equal to 2. Okay, in the question, just make a change. This shall be x equal to 3 and not 2. Now what we'll see is it is 0.5 plus 0.3t plus 0.2 p cube. This is basically the final answer which has been asked in the question. Next, take on the question. X equal to 2 has 0 probability. We just have three values, 0, 1 and 3. So probability x equal to 2 is nothing but 0. So therefore there is no term of t square. Again, in case you have any doubts in between, feel free to either use the chat box or unmute yourself and ask. Take the next question. The PGF of a discrete random variable by the PGF of a discrete random variable by is determine the probability function. Determine the probability function of capital Y. of capital Y. Give this a shot, all of you. Should be quick. So the question was that this is the PGF, probability generating function is this. You need to find the probability function of this random variable. This is nothing but PYT. You need to find this probability function of Y. So see, what you'll need to do is simply expand this, or rather, simplify this further. This is in a actually simplified form. We'll just kind of expand it. So this will be 1 plus t into 0.2 is 0.2 t square. Next term becomes 0.6 t, which is t into 0.6. Then I will have minus 1 into 0.2 t, and then ultimately minus 1 into zero point 0.6, which becomes minus 0.6. This reduces to 0.4 plus 0.4 t plus 0.2 t square. And from here, I can write this. Excuse me. I hope this is clear to all of you. Just confirm it through chat box. If it's clear to all of you, then I'll proceed to the next part. Others, is it clear? Okay, perfect then. Next, give the heading obtaining mean and variance. Obtaining mean and variance of a random variable using PGF. Using PGF. Now, before getting into this, answer all these questions first. What is d by dx of x to the power n? N into x to the power n minus 1. What is d by dx of a to the power x? So it's a to the power x by into log a. Now, just take a look at this. D by dA of right. This shall become x to the power a ln x. My only thing is we are so fixated ki the moment we do differentiation, we tend to do at a form of x to the power anything. Ki we are differentiating by x only. This was just to show ki if we are differentiating with respect to a, you just need to tree the structure accordingly. So let's say if I also had d by dA of a to the power x, this would have been x into a to the power x minus 1. So common mistake is students know what is d by of dx of a to the power x, a to the power x into ln a. What they sometimes confuse is if they are asked to mention d by d of a to the power x, you need to realize that we're differentiating with respect to a and not with respect to x over here. So the structure is, the one is of this particular form, the one which most of you might have encountered while preparing at your school level. So this is just one thing to keep in mind, which is the variable which we are differentiating with respect to. So now in all these functions, what I'm going to do is that after performing certain differentiations to the particular excuse me, generating function, those would be used for calculation of mean, variance, or any other higher moments. So if I differentiate this once p dash xt, I need to differentiate with respect to what? First of all, I am differentiating with respect to t. So when I write p dash xt, what I mean is d by dt of pxt. That is the first thing you all should keep in mind. We saw that this pxt, as we saw, this was nothing but a function of t only. And now we're differentiating with respect to t only and with not respect to x. So differentiation of t to the power x. I am differentiating this, okay. Probability x equal to x is nothing but a constant with respect to t. So when I differentiate, this will be nothing but x into t to the power x minus 1 probability x equal to x. If I double differentiate, this will be nothing but x into x minus 1 t to the power x minus 2 probability x equal to x for all values of x. Again, these are just basic differentiations. Just because we tend to work in summations and all, you might not be able to visualize it. So one easier way is, you kind of expand it, perform the differentiation, see the final result, and then try to bring it in this particular format. That is just one way. If these things do not hit you directly, might take an example, differentiate that, and then try to relate, yes, it is coming of this particular form only. So these are the two derivatives now. If I evaluate, first of all, what do I mean by this? Again, some notations which you all might not be, recalling. If I write this, what it means is first differentiate txt and then evaluate this at the point t equal to 1. So first you need to differentiate and then you need to evaluate at the point t equal to 1. Some of them, what they do is first they'll put the value of 1 and then they'll differentiate. And that might come out to be 0 because the moment, let's say you put 1 over here, things might come out to be in the form of constant itself. So keep this in mind. First you differentiate and then you put the value at which you need to evaluate the particular function. So now if you will notice, if I put the value of t over here as 1, so this becomes what? This reduces to nothing but summation x into probability x equal to x. P, this reduces to nothing but summation x into probability, and which is nothing but expectation x. So what's an easier way to find expectation x? If you have the PGF function, you differentiate that once, then you evaluate at the point t equal to 1. The numerical answer which you're getting from there will be nothing but your expectation x. Similarly, if I put 0 over here, then just take a look. Px, double derivative, what I'll be having is summation of x into x minus 1, which I can write as x square minus x. And can I write this as expectation of x square minus expectation of x? Or from here, can I write that expectation x square is nothing but expectation x was nothing but p dash x1. So from here my variance x, we know that it is nothing but expectation x square minus, and this will come out to be px double dash 1 plus px dash 1 minus px dash 1 whole square. So now what you will see is to find variance. You could think that you need to, let's say you are having three terms, right? You are having three terms over here, one term, or you need to differentiate how many times? Let's say two times. Again, how many times you need to differentiate will not be our matter of concern. Our matter of concern is if for mean, it was fine. It was just needing to differentiate it once, or rather just a single term. That is nothing but p dash x1. But to find variance, we need three terms. We will progressively see when we define moment generating function, cumulative generating function, how the number of terms for calculating, let's say, variance or skewness reduces. Yes, so we can define MGF and CGF for discrete as well. Those are valid for both discrete and continuous. As for continuous, we don't talk about the PGF itself. So this is more on the lines, some of you have this, let's say, curiosity, what was the motive of, anyone defining this function altogether. So it's all about being able to bring in a simpler, more efficient format. That was the whole intention of, whoever might have come up with the definition of these functions. Problem was how to, solve these things efficiently, and with the help of these functions, they were able to, let's say, simplify or solve this problem of interest. Let us just take say an example of one particular distribution to begin with. Let me take the example of Poisson distribution. Say x follows Poisson lambda. So first what we'll do is we'll make an attempt to find the probability generating function. So this will be nothing but expectation of t to the power x, which shall be summation t to the power x, probability x equal to x runs from 0 to infinite. Probability x equal to x will be nothing but e to the power minus lambda, lambda to the power x by x factorial. And now this e to the power minus lambda is common. I can take it outside. What I'm left with is t lambda to the power x by x factorial, x runs from 0 to infinite. And now again, throughout the session on chapters, you will see how we are using the results which we have covered in the prerequisite classes. A lot of you might not recall these from your studies at school level and all. So I have explicitly made them mentioned in the prerequisite classes. This is nothing but the expansion of e to the power lambda t. If you will take a look, what we had was expansion of e to the power x. Again, see, today I'm mentioning it. Going forward in further classes, I'll assume that you all do remember these results. If not, you could refer to your notes as well. All of these have been mentioned. Expansion of e to the power x was nothing but, let's say, t to the power x by x factorial, where t runs from 0 to infinite. So here, instead of t, what I have is p lambda. And this I can write e to the power lambda t minus 1. Now, if I differentiate this with respect to t, this will come out to be lambda e to the power lambda t minus 1, and the second derivative will come out to be lambda square e to the power lambda t minus 1. So my p dash x1, if I put the value of t as 1 over here, it comes out to be what? E to the power lambda into 0, which is nothing but 0. E to the power 0 is nothing but 1. So this comes out as lambda. This comes out as lambda square. Now my mean according to the formula is nothing but p dash x1, which is coming out to be lambda, and my variance according to the formula p double dash x1 plus p dash x1. So lambda square plus lambda minus lambda square, which again comes out to be nothing but lambda. So again, the results which we are getting will be the same only. And now you will see that this by far is a more efficient way of deriving the mean and variance as against the first principles. So whenever you have a choice, you could use, again, keep in mind in examination, do not use PGF anywhere. You need to use MGF or CGF. Till this particular part, these were just additional over and above your existing syllabus. Do not use any of the things mentioned here for examination purpose. You might not get awarded any marks for it. So this was probability generating function. Next, give the heading moment generating function. And before I proceed further, just let me, all of you let me know through chat box if you're fine with all the topics covered so far. Just mention yes, I'll proceed further. Okay, perfect then. Now first listen to me, then you all can take down the notes. I'll give you time for that. The representation of this is mxt. PGF was P, MGF is M. And cumulative, if you guess it, it will be CXT. This is nothing but expectation of e to the power tx. In case we have a discrete random variable, it becomes e to the power tx. Or a better way of this would be, and in case it's continuous, it will be integral e to the power tx fx dx for all range of x. This is in case we have a discrete random variable. This is in case we have a continuous random variable. Now, one further property which we see is if I take a look at mx0, this will become nothing but expectation of e to the power 0 into x, which is nothing but expectation of e to the power 0, which will be nothing but expectation of 1, which is nothing but 1. Instead of t, I am putting the value 0. So 0 into x is 0, e to the power 0 is 1, expectation of a constant is nothing but 1. You can also see from here, if I put t as 0, this becomes nothing but what? E to the power 0, which is nothing but 1. So I am integrating PDF in its entire range, the value of which is 1. So the result which we use is mx0 is equal to 1. Keep one thing in mind for PGF, you saw we were trying to evaluate at the point t equal to 1. You might again have this thing in your mind, why in PGF we were doing t equal to 1. We'll get the results, but you might wish to wonder why it was t equal to 1. And here, or even in CGF, we will be putting t as 0. The reason that is, once we try to expand it, we want to eliminate the terms of t. When we need to find the mean, variance, skewness, anything, it is in terms of what? Expectation x or x square or x cube, so on. We do not want any value of t. Given the way we have defined the probability generating function, this term, I need this to be removed. When I say removed, it doesn't mean you put it as 0, because 0 into anything becomes 0. I want this term to reduce to what? 1. The way to do that is if I take the value of t as 1, because 1 to the power anything non-zero is 1 only. And here, given our definition of MGF, this will happen when I will take the value of t as nothing but 1 over here. then only results will come in. That one we will shortly see. Here, when I put the value of t as, sorry, not 1, when I put the value of t as 0, then we basically get results which are giving us, let's say, the mean, variance, higher moments, so on. So all of you take this down. Shruti, your question is, in this case, the mean and variance will be same. This is in reference to which question? Feel free to unmute yourself and ask.
So the thing which you explained, X follows Poisson distribution.
Yes, so for a
Lambda.
Poisson distribution, we had already covered in probability distributions as well. The mean and variance is same only, and that is the result which you are getting over here as well.
Okay.
All the results you get here are going to be consistent with what you get from using first principles. I hope all of you have taken this down. Next, here. Limits depends what values x can take. If it can take the values minus infinite to infinite, so it will be minus infinite to infinite. This basically means for all values of x. Now, if you will remember, e to the power tx, mxt is nothing but, excuse me, expectation e to the power tx. E to the power tx can be expanded as 1 plus tx plus t square x square by 2 factorial. So now if I break them, first term will come out to be 1, then t into expectation x plus by 2 factorial expectation x square, so on. So from here, what you can see is coefficient of t to the power k by k factorial is expectation x to the power k. The coefficient of t to the power k by k factorial is nothing but expectation of x to the power k. This is MGF, sub specific. PGF mein there were different things. MGF we are working differently. There we were looking at coefficient of t to the power k only. Here we are looking at t to the power k by k factorial. There we were getting probabilities. Here we are getting moments. That is why the name is moment generating function. It is generating nothing but the moments. Expectation x square, expectation x cube, and so on. Next, let us say attempt to find MGF. Let us take two examples. One we'll take off again Poisson. Next we'll take off gamma. Again, note that while we'll be referring to the institute material, you will find several examples. So that is something I'm leaving for you all for practice. This is the simple formula. You need to apply it accordingly to different distributions to get the particular result. Keep in mind in your actual tables, instead of this is a more technical form of writing a MGF. Alternatively, one can also write as MT. This just makes it sure that the random variable of interest is x. Here, it is automatically being implied as in whatever random variable you're defining, be it x, y, or z, it means that only. So in actual tables, I guess they have given it in this format. So MT stands for nothing but MGF, and if they have written just PT, this would be referring to nothing but the PGF. Now, let us attempt to find the MGF for a Poisson distribution first. Again, these are very straightforward. We'll try it for Poisson as well as for a gamma distribution. So this shall be MGF is expectation of e to the power tx, and this shall be summation e to the power tx, e to the power minus lambda, lambda to the power x by x factorial. X runs from 0 to infinite. I can take e to the power minus lambda common, and I can recombine to write this term as e to the power tx into lambda to the power x can be written as lambda e to the power t whole to the power x. And this will be nothing but which can be written as e to the power lambda e to the power t minus 1. Again, take out the steps inward and see if it is making sense to you or not. Next, we are going to do that for a continuous distribution. Let's say gamma distribution. So my mxt will be integral e to the power tx, and the PDF of a gamma distribution is this. In case you do not recall it, you could refer to the actuarial tables for same. Now, just one thing we all need to be careful while performing this integration is, take a look at it. We are integrating with respect to x. Well and good till here. These terms are independent of x. We have taken it outside. Now, if you will see, what we are getting is nothing but a form which is of a gamma integral. And we know certain results of gamma integral as well. If you would remember or if you would refer to, this was the result of gamma integral. Now here alpha was positive, lambda was also nothing but positive. So the coefficient of x was positive. Now here lambda to the power a by gamma a. Note that this integral will be only valid if my this entire term is positive. That is t is less than lambda. If t is less than lambda, then only this term will be positive, and then only this term comes in the form e to the power minus x into some constant, some positive constant. So now this shall become gamma a by lambda minus t to the power a. And this condition will carry additional marks that this results only when t is less than lambda. Gamma a cancel out. What we're left with is lambda by lambda minus t to the power alpha. And we can also write this as lambda minus t by lambda to the power minus alpha. X can be written as nothing but 1 by x. 1 divided by of 1 by x. We can write a by b, nothing but b by a to the power minus 1. And this can be further simplified to 1 minus t by lambda with the condition in all the steps, or rather, after giving over here, in the final step, do give this as well. That this MGF shall only be valid when t takes a value which is less than lambda, else it will not make sense. Next, give the heading obtaining mean, variance, moments using MGF. Using MGF. Now note that you can take either the random variable to be discrete or continuous for derivation purpose. I am taking it to be continuous and showing the derivation accordingly. This will be e to the power tx fx dx 0 to in whatever be the limits. Now I am going to differentiate both sides with respect to t. What is the differentiation of e to the power tx with respect to t?
X e to the power dx.
Differentiation of e to the power tx with respect to t is nothing but x into e to the power tx, and fx is a constant. Similarly, if you will see, if I differentiate it twice, I'll be left with nothing but x square. So, if we'll see, if I differentiate n times, this will be nothing but and now if I, let's say, evaluate this at the point of 0, e to the power tx, this entire term becomes e to the power 0, which is nothing but 1. I am left with nothing but integral x fx dx, which is nothing but expectation of x. Similarly, my m, if I differentiate this n times, again, this is not the correct notation, dn mxt by dtn evaluated at the point t equal to 0. This will be nothing but expectation of x to the power n. So now for calculating variance, I need ex square Now, what I'm trying to show is in case of PGF. Okay. Now, note that this formula is true whether it's a continuous or a discrete random variable. Just for purpose of showing all, I've taken it to be continuous. You can take to be discrete, exact same result will be coming out. In variance term, how many terms do we have? 2 terms. In PGF, we had 3. And next we'll see in CGF, there is a single term itself. So if one could ask, why after defining one function, defining other functions, because they are becoming more and more efficient. So take this, all of you. That is T. Take this question. Mxt is equal to 1 minus 4t to the power minus 2. I'll be only solving it using two methods. So when I say two methods, see, one method for calculating expectation x to the power n is you keep differentiating it at times and evaluate at the point t equal to 0. Alternatively, I also saw that I can express my MGF in this particular format. And once I do that, the coefficient of t to the power k by k factorial is nothing but expectation x to the power k. Now we will see in certain places using this concept will help us to find the answer in a easier way, and in most of the cases it will be, let's say using this particular one. So that is why we are covering both of them. Expectation x. So first, let me differentiate. What shall it be? Minus 2, 1 minus 40 to the power minus 3 into minus 4, which will come out to be 8 into 1 minus 40 to the power minus 3. And if I put the point t as 0, this will come out to be 8 into 1 minus 4 into 0 to the power minus 3, which will come out to be nothing but 8 into 1, which is 8. Fair and straight, here the differentiation was easier. But if I want to find expectation x to the power 6, how many times do I need to differentiate? 6 times. That here, not very much messy, but in certain cases it can become extremely messy. So another way you could do is just find expectation x to the power 6 by differentiating it 6 times. You will get the answer. Another way is if I express this is nothing but an expansion of a negative binomial term. Again, something which we had covered in, let's say, the prerequisite classes. So my MGF can be expressed as first term here is going to be 1. Next term, this will be 8t. How 8t? It will be basically what? If we'll take a look at expansion of 1 plus x to the power p, it is 1 plus px plus p into p minus 1 x square by 2 factorial, so on. Instead of x, what I have is minus 40. Instead of p, what I have is minus 2. So this will simplify. Next term will be 80, 2, 3, 4, minus 2, minus 3, minus 4, p minus 1, p minus 2 into minus 4t whole cube by 2 factorial, 3 factorial, 2 factorial. P into p minus 1. So this is the second term. So this shall be similarly, next term will be minus 2 into minus 3 into minus 4 into minus 40 whole cube by 3 factorial, so on. So if we'll see the coefficient of t to the power 6 by 6 factorial will be nothing but what? Minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. When it's 2 factorial, it's a 3 over here. So when it will be 6 factorial, from there you can see it will be minus 7. Okay, you can or just put it here, get the term, or you can observe the pattern and minus 4 to the power 6. This can be written as 2, 3, 4, 5, 6. Even number powers, this will simplify to 7 factorial into 4 to the power 6. 2 into 3 into 4 into 5 into 6 into 7. This will be nothing but 7 factorial into 4 to the power 6. And you can calculate this using the calculator. There is no easier way than this. Either differentiate 6 times or find the pattern and get this. No other alternative way. Another method using MGF, this is the way. Or another way if you want to do is you can use the result expectation x to the power 6. You can identify that this is nothing but MGF of gamma distribution. Just take a look. We did not did. Take a look at the MGF of gamma distribution. 1 minus p by lambda to the power minus alpha. Lambda is nothing but 1 by 4 and alpha is nothing but 2. So you can identify that this is nothing. X is nothing but a gamma distribution with parameters alpha being 2 and lambda being 1 by 4. Once you know that, you can use the results available in actuarial tables to find expectation x to the power 6. Next, give the heading uniqueness property. Uniqueness property. If a MGF has been formed, if a MGF has been formed, comma, then there is a unique distribution. Then there is a unique distribution associated with that MGF. Associated with that MGF. Full stop. Thus, a MGF. Thus, a MGF can be recognized. Can be recognized as the MGF. As the MGF of a particular distribution. What it means is each distribution has a unique MGF. Alternatively, if one distribution, if we have a particular MGF, it will correspond to a unique probability distribution only. So how we use this result is if two random variables have the same MGF, then they must have the same distribution. And we will see how we use about this. We will take a look at this post this after completing CGF. So you can just take this down. Next heading, CGF. Next heading, CGF. We denote it as CXT. And this is nothing but simply ln of mxt. Just take the log of MGF and that is nothing but CGF. And now what we are going to see is that to find the mean, C dash x0 will give us the mean. C double dash x0 will give us variance. And C triple dash x0 will give us skewness. So the easiest way, I would say, most of the times to find mean, variance and skewness is to find the CGF, differentiate 3 times, first time mean, second time variance, third time directly skewness. We can get into the derivation of this. I will just get into derivation of one. Others you could do it accordingly. It will just be testing your ability to differentiate. If I differentiate d by dt of cxt, here I need to apply what? Chain rule. I am differentiating a log function. So this will be 1 by mxt. Remember that differentiation of log x is nothing but 1 by x. Here it is ln fx. So 1 by fx into f dash x. That is. And now when I evaluate this at the point t equal to 0, I am left with m dash x0 by mx0. And if you will see, we have quoted the result that mx0 is nothing but 1. Next, let's try variance as well. So C double dash x t. Now you will need to apply u by v method. We have m dash xt by mxt. So first I keep mxt constant and I differentiate this, which will be m double dash xt minus, when I keep the numerator constant and I differentiate denominator, I get this term divided by mxt whole square, which reduces to mxt m double dash xt minus m dash xt whole square by mxt whole square. And if I value this at the point 0, then C double dash x 0. I am skipping some steps over here. Just take a look once. Mx 0. First term will be nothing but 1. Next, what I have is m double dash x 0. Here, what I have is, and denominator becomes nothing but 1. This is nothing but expectation x square minus expectation x whole square, which is nothing but variance x. And again, starting from here only this step, again it will be even more complicated. You can attempt to find skewness. Can differentiate further, apply, it will come in a format which will be nothing but formula for skewness itself. Final heading for this topic: linear function of x. Linear function of x. Say we have y is equal to a plus bx, where a and b are constants, x is a random variable. What I'm trying to do is, I will try to express, say, mgf or cgf of y in terms of mgf or cgf of that of x. So if I start with m by t, this will be expectation of e to the power ty. This will be expectation e to the power t a plus bx, which I can write as e to the power bt, e to the power at, e to the power btx. Note that e to the power at is nothing but constant. And what I'm left with expectation e to the power btx, which I might also write as mx. mx t is t into x. What I have is bt into x. So instead of t, I can write this as bt. And my CGF then is nothing but what? ln, which will be ln of e to the power at mx bt. Now, if I will remember, log AB is nothing but log A plus log B. ln of e to the power at plus ln of mx bt. This is nothing but at plus cx bt.
Using y makes it x.
Using the results of x, we can get the results of y. We're expressing everything of y in terms of x. Again, these results you wish to remember, fine. If you do not wish to, what is main important over here is the way to progress. If you can express a random variable a plus bx, then you know how to go about finding the mgf or the cgf for y. But take down a result. These are certain important results. Write down. Uh, addition of IID, addition of IID. What I mean by IID is independent and identically distributed. Addition of IID, exponential random variables, gives us a gamma random variable. Gives us a gamma random variable. Now you prove this as well, okay? Using MGF. Let's say I define y to be x1 plus x2 so on plus xn, where xi follows nothing but exponential. All of them are independent, all of them are identical, they are following same distribution. What I will ultimately show is y will be following a gamma distribution with parameters n and lambda. How to bring that? Through MGF. We are going to use which result? Uniqueness property of MGF. That is, if I find a particular MGF, it corresponds to a specific type of distribution. So MYT will be nothing but expectation. All of you take a look. E to the power ty, which I can write as e to the power t x1 plus x2 xn, which I can write as e to the power t x1, e to the power t x2, e to the power t xn. Now, given all of them are independent, I can write them as, because they all of them are independent, xi's are independent. Next step, since all of them are identical, this will become what? Expectation of e to the power tx. How many terms are there? N terms. And this becomes nothing but mxt whole to the power n. And now, if you will take a look at the MGF of an exponential random variable, it is 1 minus t by lambda to the power minus 1. We take it to the power of n, which is 1 minus t by lambda to the power minus n. And this corresponds to nothing but the MGF of a gamma. So here, this is the entire derivation. If they ask you, show that the addition of IID exponential random variables gives us gamma, this is the way to go about it. We found out the MGF of y. We are getting this structure, and we know this corresponds nothing but to a gamma distribution having the parameters n and lambda. Now again, the way to go about is in class we have practiced, let's say 2 or 3 distributions. I will say try to attempt as many distributions as possible which are there. We have covered in chapter 1 in probability distributions chapter, so that you do get a bit familiar with the final results. They are already there in the actual tables, but if you practice it yourselves, it might be easier for you all to recall it. This is all we have in this chapter. Ultimately, if you see, we have something called PGF, MGF, CGF. As part of syllabus, it's mostly MGF and CGF. How to go about calculating mean, variances, skewness, etc. And final part is using the uniqueness property to find or identify distributions of certain random variables. Second last step. This one are you asking, Akash? If you will refer to tables, the MGF, MXT, X is nothing but exponential distribution. You will see that the MGF of exponential distribution is given to be 1 minus t by lambda whole to the power minus 1. You could derive as well separately. Here I'm just using the result. It's there in actuarial tables. And remember that x to the power a to the power b is nothing but x to the power ab. So there's a minus 1, there's an n, which basically simplifies to minus n. So that's all we have for today's class. Any doubts with respect to today's class?
Exponential is special case of gamma.
Hmm?
Exponential is special case of gamma.
That is one way to say exponential is a special case of gamma where the parameter alpha takes the value 1. Alternatively, another result is addition of n independent identical exponential random variable gives us a gamma distribution.
For the MGS.
Okay, so this is the proof using MGF. Let's say if we had covered, if you would remember, adding Bernoulli gives us binomial, adding geometry gives us negative binomial. Okay, there we could explain intuitively how we were getting the results. Here intuitively we can't, so we need to take the use of what? PGF. Or sorry, the MGF. Then that's it for today. Thanks everyone.